Hi everybody, good morning and welcome to the AWS IoT Rules Engine session. My name is Itamar Cohen and with me today will be Yuval Fernbach, a solutions architect from AWS, and we have Arnold Meyer, who is a business development manager from TomTom Maps, and Yussi Koski, director of enterprise telematics IoT from Here Technologies. And today we're going to be talking about the rules engine, but overall we'll do a review of it. Then we'll talk a little bit about how to write rules in the rules engine, what you want to take into account in these rules. We'll talk about enrichment of IoT data, especially through the rules engine, how you would do that and why or when would you want to do that. And we'll talk about geolocation in IoT, why it matters so much in IoT, and these two gentlemen will talk to us about a few ways that we can embed geolocation in IoT applications. So to start, I don't know how many of you know this, but we see IoT as having three pillars. We have the devices pillar on the left, which is the devices themselves that are in the field, they produce actions and they send data. Then we have the cloud pillar, where we manage the devices, manage the connection, and also we pass information to the intelligence pillar, where we go and apply logic on data that devices send, produce insights, and use these insights to eventually drive actions. Today, we're going to focus on the place where cloud kind of meets intelligence, or more specifically, if we look at AWS IoT Core, our platform to connect devices, then you would see that a device connects to the device gateway, which is on the left, and the device gateway uses data on the device from our device registry service to authenticate and authorize the device, and then passes on messages from that device to our message broker. Our message broker then distributes these messages over to other devices, to a service that we have called the device shadow, which is used to maintain device state in the cloud, and to the piece that we will be talking about today, the rules engine. So what is the rules engine? The rules engine is a service that allows you to connect devices, apply logic on the data that they send through filtering and transforming device messages, and then to drive actions in a set of AWS and non-AWS services. Over here you see some of the AWS services that we support, and Salesforce, with whom we have a strategic relationship, whom you can also drive actions in directly from the rules engine. You can also use some of these services to drive actions in other AWS services or even in external endpoints by using Kinesis or using Lambda or SNS. And how do we do that? So in the filter and transformation piece, we do it by applying SQL on the device messages. We take into account that the device messages will be in JSON format, and then the select piece is through selecting the fields that you want to pass on from the device's message. Then the from is which topic the rule will be listening to, and eventually aware, which is which conditions are there to pass on the message forward. For example, in this example that you see up there, we are only taking the space ID from the device message, and we are doing it for messages with the topic of IoT temp sensors, and only when the temperature that was in the message was above 50. Now, in the SQL, you can use an array of functions that we have. We have some string and mathematical operations. You can get the shadow data of a shadow document. You can call the predict function from an Amazon machine learning model that you've trained, and a bunch of other more generic functions. And to showcase this, Yuval here has built us a demo. In this demo, we are showcasing reInvent, the reason we're all here. And I don't know if any of you noticed, reInvent quite grew in the last 3 years. We have over 6 venues and tons of activities to do. So we are simulating a device that could one day go on the shuttles that we have at reInvent, where this device would tell you on the shuttles about cool and interesting activities that you can take part of at reInvent. Now, I want to point out this is a simulated device, hence this is not the reInvent shuttle. If you see the shuttle, please don't go on it. And for this demo, we're going to look at the following use cases. We're going to look at simply sending the device data and usage data into the cloud. We're going to recognize who's using the device. We're going to track where the device is and take actions according to that. And we're going to find what the ETA is for the device to various activities. So Yuval, why don't you tell us how you were able to build this?
Thanks, Itamar, and good morning, everyone. This is the architecture of the demo we've built to demonstrate the different abilities of the rules engine. As you can see in this demo, we used this device, this Raspberry Pi that you can see here, to simulate the different shuttles on the Las Vegas Strip. And this device sends data into AWS IoT. During this demo, we'll focus on the different use cases that Itamar showed before, and we'll show how we managed to solve those different use cases. We also built a website to show you the shuttles on the map and to change the configuration of the shuttles. So let's see the website that we've built. You can see it? Great. As you can see, this is the map of Las Vegas, of the Las Vegas Strip. Here you can see the area, and you can see here, up here, the Aras and all the different hotels. And you can see that right now I have 2 shuttles on the map. Again, those shuttles are simulated. Those are not the real shuttles of this event. In the right, you can see that I can change the different configuration of the shuttles. During this session, we will change the different configurations and show how the rules adapt to the change configuration.
Thanks, Yuval. So for the first use case, why don't you show us how we were able to implement sending telemetry and usage data from the device and how you chose to store it?
Thank you. So we wanted to get the telemetry data from the device, from this Raspberry Pi, and to query the location of the shuttles on the map. For this, we decided to use Amazon Elasticsearch Service due to Elasticsearch Geo queries abilities. The problem was that Elasticsearch expects to get geo points in a specific format, actually in a nested JSON format. And the device itself sent the data in different formats. So you can see on the left the format that the device sent the data in. And in the right and in the left, you can see the format that Elasticsearch expects. How can we change the format from the one on the right, on the left, to the one on the right? For this, we use the rules engine, and we created this rule, as you can see on the bottom. This rule queried the data from the left format, and then show it as the one in the right. You can see, for example, on the third line, the current position lon. In the current position lon side, you see that we save it as location.lon. That creates this nested JSON format that Elasticsearch can receive, and then we can use Elasticsearch Geo query abilities to show those shuttles on the map. So this is the only rule we used. We used to change the data from the one on the left to the one on the right. Then we just sent it using an action directly into Amazon Elasticsearch service.
Thanks, Yuval. For the following use cases, we want to talk about a new feature that we launched last week in the rules engine. So as we saw previously, rules engine allows us to apply logic on messages and then drive certain actions in the cloud in various AWS and non-AWS services, which include Lambda. We added the capability to call a Lambda directly in a rule, SQL, and then use the results of that Lambda to enrich the data and forward that to whatever action you choose to take. How do we do that? So you can use that either in the select clause if you want to, for example, enrich the data that you're going to pass forward. In this example, we are taking the space ID from the previous example, and we are using a Lambda to turn it into the space name that we will be passing forward to the action. In the next example, we are doing it in the where clause. So if you want to get some more data to know which messages should be filtered, you can call a Lambda, and in this case, we are querying what is the maximum allowed temperature for this space, and we're only forwarding the message if the temperature is above that maximum level. One note is that we capped lambdas at 2.5 seconds because we don't want rules taking too long. Why would we do that? So one option is if you need to apply more sophisticated logic in a rule than what SQL allows you. Another, and a very popular one we've seen, is to enrich data that comes from IoT, something that we see happening a lot for IoT data. And we see that happening either from customer data services, where the customer puts in the data, such as ServiceNow, SAP, or Salesforce. When we see it from what we like to call general data services that kind of describe the world or certain world systems. This could be here and TomTom, whom you'll hear from soon. This could be Dark Sky, who do weather reporting, or the NIH for health data. And also, you can pretty much enrich from any AWS service. So you can apply some logic from Amazon Rekognition. You can call any Amazon API gateway function, or you can query various AWS databases to get contextual data. And for this, Yuval, I understand you used this capability to attack the use case of recognizing users and logging what they reviewed.
Yes, thanks, Itamar. So we wanted to demonstrate how can we use an in-SQL Lambda to enrich the data that comes from the devices. And the second use case was how can we recognize who goes in and out of the shuttles? How can we use the different sensors that are already in this device to enrich our data with the username? For this, we decided to use this camera that is already part of this Raspberry Pi. So we wanted to take a picture of each user that go in the shuttle. Again, it's only a demo. And out of the shuttles, recognize who is this user, enrich the data with the username, and then save this data in DynamoDB and send a notification using SNS. Let's see it in action. You can see the map here. So I will start by capturing my picture. Let's see. And I will, just a second, sorry. And I will go back to the AWS IoT console. Let's see that I get this message. OK. As you can see, when I capture the picture, I sent a message from the device. This message includes the base64 encoded picture that I captured. You can see it in the payload. Then I created a rule. The rule takes this data and pass it to Rekognition. Let's see the rule. Here you can see the rule that I've used. I will just show you the SQL itself because it will be easier to understand it. So this is the rule I've used. You can see that this rule selects the event ID. It uses the data and the operation. In this case, the operation is compare, and send it to an AWS Lambda. This Lambda called Recognition Enrichment. Then it takes the response of this Lambda and show it as name. It takes this data from the topic camera / reinvent / hash, any topic after camera / reinvent. Let's see the Lambda function. This is the Lambda that I wrote. Let's go down here. You can see that this Lambda get an event. You can see it in here. So it gets the event, the JSON, from AWS IoT. Then, if the operation was compare, it sends the data to this function I created called search face. This function is just called recognition to get the image ID of the user of the image that I already registered in the device. And then it gets back the face matches from recognition. After I got a message with matching faces, I could use this data, take the username from my database, and respond back with the username of the user that just got in to the shuttle. So you can see that I return the username that got into the shuttle. I'll go back to the website, and you can see, I push it a couple of times, but you can see that I'm now in shuttle 2. So this camera took my picture, then recognition enriched the data with my name, and then I saved it into DynamoDB and sent a notification using SNS. This is one of the ways that you can use in SQL Lambda to enrich your data with the response of the Lambda function.
Thanks, Yuval. And the next use case we want to take a look at is when we track devices' location. Now, one thing that we've noticed is that a lot of times IoT devices don't necessarily have a GPS installed. So for this demo, we focused on how would we figure out where the device is, even if it doesn't have a GPS, and then how do we take an action based on the location of the device afterwards. So, Yuval.
Thank you, Itamar. So those devices, again, we wanted to use different sensors that are already in the devices. And in the device, we also have Wi-Fi on the device. And we can use this Wi-Fi to scan for the different wireless LAN in the area. We decided that when we send data, the location of the device, we'll also send the wireless LAN in the area. And then, for devices without GPS, we can use here geopositioning API to get a location from the different wireless LANs in the area. So how did we build this use case, this feature? As you can see, those devices send the data with the location and with the wireless LANs in the area into AWS IoT. Then we pass this data to here's API using an in-SQL Lambda. We get back the location of the device, and then we can keep things as normal. We can save this data in DynamoDB, we can send it to Elasticsearch, etc. Let's see it in action. As you can see, just a second. Each one of the devices send the data of their location and the current position wireless line, the current wireless line in the area. You can see here the current position. This is the longitude and the wireless LAN. Let's turn off the GPS on this device. And now look back at the data that I get from the device. Now you can see that the current position longitude is 0. So this device currently don't have a GPS. It can't send me the location of the device, but it keeps sending me the wireless LANs in the area. And if I'll go back to the map, let me just show you the rule. So you can see that I created a rule called position enrichment. This rule gets the location of the device, the wireless LANs in the area, and send it to here's geopositioning API. Let me show the rule like this. So you can see that I use the Lambda. This Lambda gets the current position wireless LAN. You can see it on the bottom of the first SQL, so I will just mark it. And then it saves the response of the Lambda. Again, all the Lambda does is send this data to here's geopositioning API. The response of this Lambda we save as location. Then we can just send this data to Amazon Elasticsearch Service and see this shuttle on the map. If we'll go back to the map, we'll see that this shuttle 2, still moves. We can see that the location of this shuttle keeps changing, although we saw that the messages don't contain the location of the shuttles. Okay? So this is one thing that we wanted to do. The other thing is that we wanted to do something when the shuttles go out of the strip. We want to know when the shuttles go out, and maybe change the configuration of the shuttles. Maybe we want that the telemetry data will be sent only once a minute and not each 5 seconds. We also want to get a notification each time that the shuttles leave the strip, because maybe you shouldn't do it. For this, we also used here's geofencing API. So let's change the device location. Again, it's only a simulator, so I can just change the device location and tell it, now simulate that you are off the strip. And now when I change this configuration, let's just wait a few seconds. and zoom out. OK. This device changed its location. And you can see that I received an event. This shuttle is off the strip. How did I receive this event? I created another rule. This rule that you can see right now at the bottom, okay, this rule over here, get the device location, and then it checks if the device location is valid. So you can see the lambda at the bottom, at the where part of the SQL. We take the device location, send it to a lambda function, to an in-SQL lambda function that reach out to EAR's geofencing API, receive back if this device location is valid or not, according to a polygon that we configured in EAR's API, and then check if this device is valid. If it's valid, everything works fine. If it's not valid, then we send an event, and you saw it on the map. To learn more about EAR's geofencing and geopositioning APIs, we have here Yussi Koski on stage. Yussi, come on here.
Good. Thanks, Yuval. And good morning, everybody. So I will talk to you today briefly about how to develop location-based IoT apps leveraging technology from here. And you might know here as a mapping company and a global mapping company. And that's OK, because that's what we've been doing for the last 30 years. We've been mapping the globe. And now I think we can happily claim and say that we have reached the initial objective, that we have actually become a truly global mapping company. We're offering maps in over 200 countries, have feet on the ground geospatial experts in around 100 countries in the world. We're powering 4 out of 5 cars that drive with inbuilt navigation system. We are providing the maps or location services for those. And we are also running a set of cloud services, location APIs, as a cloud service on a global basis. And to run that in a massive scale and serve all the big customers, we have partnered with AWS to run our services on the AWS cloud. But going forward, when we are moving to high-definition maps to power highly autonomous driving and autonomous world in more general, we are actually becoming more like a location-focused big data company. And why is that? It's largely related and driven by IoT. If we look at not that distant future, we see that there will be roughly 10 billion people on this planet. We will have 2,000 megacities that will be really battling with congestion and sustainability of the infrastructure. We have drones delivering packages via regulated flight paths. We will have robotics, artificial intelligence, data analytics. And basically, every physical device is going to be connected and exchanging data in the internet. The challenge is that a lot of that data is typically siloed. And this big data is messy, and it's difficult to leverage that data. But we feel that there's some hope. I just read an analysis, an analytics study, which is saying that over 70% of the collected big data is actually having location as an identifier. It has some type of a location identifier. And actually, location is really a logical way to connect the data together, orchestrate it, organize the data, and actually enrich and get really the value out of the data. And that's what here intends to do. So here are examples and 4 steps on how you could actually enrich the data from IoT devices using location data and location services. The first step, as you well mentioned, is understanding where the device is, getting the X, Y, and in some cases also the Z coordinate of that device. The second step is to understand better the context of that device, converting with geocoding technology that XY into a human-readable and human-understandable address, or understanding what is actually the logical place on that address, like a hotel area in this case. or understanding what is around that device, what other services, what other devices are around there. The third step is to react in real time then to that data. For instance, using geofencing and understanding if the device is in a certain location and inside a certain geofence, or calculating routes, drive times, or ETAs from that location to another given location to enable use cases, for instance, like picking up the optimal delivery vehicle to pick up a package which is on a certain location, by first understanding which are all the vehicles on your fleet inside that drive time area, considering traffic information and the type of a vehicle, and then selecting the optimal vehicle to pick up the package. And then the fourth step is actually taking the big data that you collect and visualizing it on the map to get more insights. And it's already good to plot it on top of the map as a heat map, because then you can start seeing patterns on your data. But things get really interesting when you actually reference that data into the objects on the map, like for instance, to the buildings and to the streets, to really see that what is the activity inside those buildings. And then you can start filtering and then doing further analysis. Now I'm going to briefly talk about the two services that Yuval was demonstrating. First, the network positioning, which is basically providing a global positioning service by listening to all the radio networks around. It can be Wi-Fi networks, but also mobile cell ID networks, or mobile networks, cellular networks, or any beacon infrastructure. So we are basically technology agnostic, listening to that radio infrastructure and triangulating the position based on that. This is enabling positioning with the devices without the GPS, but it's also complementing the use of GPS in the devices by providing better accuracy and then also allowing the devices to work also indoors where the GPS doesn't work, so that you can build actually applications that work seamlessly outdoors and indoors. This is available via REST API, but then if you integrate some of the client-side libraries, you get also additional benefits like reduced power consumption and capability to build services that work also offline. When you want to build the IoT apps, you don't want them to be restricted to work only on Las Vegas Strip or let's say Bay Area. So you want it to work globally. And like all the services that we provide, also the network positioning API, it provides a global coverage. So as you can see, the coverage is basically following the population on this globe. Currently, we have on our database around 3 billion Wi-Fi hotspots and over 100 million cell IDs. And that database we're keeping up to date with crowdsourcing and massive machine learning capability, which is basically providing updates on a daily basis. Yuval was also demonstrating our geofencing capabilities. And there you can understand if your device is entering or leaving a geofenced area. If you want to build use cases, it's important that the geofencing capability scales to different environments so that you can, for instance, send an ad when a person is near a certain location, or traffic alerts or hazard warnings when somebody is on a road segment. Or then, for instance, understand which ones of your service vehicles are on a given neighborhood inside a city. That's why our geofencing is providing different type of out-of-the-box geofencing capabilities. So you can basically upload any number of radiuses, circular geofences, or custom polygons. Or you can use some out-of-the-box features based on the location services that we provide. You can, for instance, use any admin area on the map, like a zip code or a neighborhood boundary, as an out-of-the-box geofence. You can calculate route and then use that corridor along the route as a geofence. Or you can calculate a travel time area. What are all the locations that you can reach in a given time frame? And then you can use that as an out-of-the-box geofence. So these are some of the examples how we are helping to make sense of the data and making sense of the world using location services. And if you're interested, I'd recommend you to go to the developer.here.com website to learn more about the APIs that we provide. We have some basic APIs starting from core location services like mapping and geocoding to more advanced features like data visualization on top of the maps or specific enterprise advanced routing features. So that's it from my side, and I'll hand it over to Itamar.
Thanks, Jussi. So for our final use case, we are going to look at the ETA of the shuttles to different reInvent activities that we will be able to show on the device. So we will know when a customer would arrive at a certain activity, and also so we can take certain actions if a customer is going to be late. Yuval?
Yeah, thank you. So again, we wanted to get the estimated time of arrivals of each of the shuttles to each of the venues. We already know where each shuttle is, and of course we know where is each of the venues. So what we wanted to do is to enrich the data of the telemetry data with the estimated time of arrival according to a specific route. For this, we decided to use TomTom Maps routing API. So we just send to TomTom API the location of the device, the route that this device do, and then we receive back the estimated time of arrival to each of the different venues. Of course, this estimated time of arrival is based on the traffic that is currently on the road, etc. Let's see it in action. Let me just move back to the map. You can see the map, yes. So you still see this shuttle moving on the strip. I created a rule, let me show you the rule, that gets the location of the device, sends this location to a specific lambda called ETA enrichment, and receive back the ETA for each of the different venues. So you can see that you can see it in here, that I receive the data from the lambda and mark it as ETA. Then I can save this data in a database and can see what is the estimated time of arrival to each of the venues. So if I'll go back to the map, you can see that when I click on a shuttle, the estimated time of arrival of this specific shuttle, again, it's only a demo, is on screen. And I know that this shuttle is going to get to the Bellagio at 9:21 a.m. To learn more about the different routing and the APIs of TomToms, we have here Arnold with us. Arnold?
Thank you, Yuval and Itamar. Yeah, so I'm Arnold Meijer working at TomTom Maps. And IoT is going to change the way we use maps. It's going to change the way we build maps, and it's going to change the way you implement maps in IoT. Maps and map software have always helped us move around and guide our way, and now for IoT, it will do so as well. IoT devices give you the ability to find the location based on the connectivity of the device. Think about locating the nearest taxi, or finding a way through the network for your assets, maybe a container, or tracking the maintenance of the location of your road infrastructure. Now, all these kind of use cases create a massive demand for location, but it also puts a massive stress on the maps that go in it. And the reason for that is that map information is traditionally built in a slow and manual way. Most of the map platforms and systems that we see are dependent on those kind of manual systems. And that's not in line with the kind of IoT use cases that you want, where devices are continuously moving. But what if you could use IoT actually as a way to build maps? What if you could use the dynamic nature of IoT to create maps that are built in a real-time and dynamic way? What you see here is a map of the world, not a map as we see it, but a map as we use it, as devices move around. Every single dot on this map is a movement of a device. And what you see is that the more devices move, the more traces they give us, and the more information they give us about the world around us. It allows us to build maps in a dynamic way and feed that information back to map platforms and IoT platforms. Now, as I said, IoT is a use case where everything is continuously moving. So of course, this is not static. It's something that you can do in a real-time manner. So let's take a look at San Francisco. So in the morning when San Francisco wakes up, what you see here is actually traces from over 500 million different devices that tell us things about what's going on in the world. Think about the use cases that you saw today. Finding the fastest travel time, or ETA, depends actually on understanding if roads are still open. Is there a roadblock? What's traffic on my way? If you want to find the right location for a certain asset, you have to understand, well, is that location actually accessible? And using IoT as a tool to understand those kind of things about the network helps you build map information and map software and feed that back to IoT platforms. So that's something that we rethought at TomTom Maps. We said, what if you can use maps in an easy-to-use way in APIs and SDKs for IoT platforms? And we did that. And today, together with AWS IoT, it becomes easy to integrate that kind of real-time data in your application. So let me explain you why by giving a description. So there's 3 basic questions that you are thinking about when you're using location and IoT. The most critical one, or the starting point, is what's my location? Understanding where the device is a crucial step in building your application around it. But quickly comes the follow-up question, and that's, what do I know about my location? Because if I only know my location, I cannot make a well-informed decision. But as soon as I know what my address is, the business that I'm in, the venue, maybe the administrative area, I can make a better informed decision for that device. And then finally, you want to take action on that. So you want to know, what's my position compared to other locations? So that means understanding, what are these other locations? Maybe it's static locations in the map, but maybe it's the other IoT devices in your pool of devices that you want to see moving on the map. So it's about a couple of basic things. That's understanding those locations, but also what's your position relative to those kind of other devices and locations, which you can determine based on ETA, travel time, or distance. I'll give you 2 examples of how that works, but also on how customers actually use that in their IoT applications to be successful. So the first one is the search API. When you think about searching around your location, there's a couple ways to do that. The first one is searching by radius. In mapping, we call it as the crow flies, which means that it's the quickest way to get to a destination with an abstract distance. That can be relevant to certain use cases. Think about air pollution, but often when you talk IoT devices, there's movement involved. There's limitations in the geography around you. So that's often where a polygon search comes in. So by searching in your API in a polygon, you can use that, for example, to search within a certain administrative area. Think about searching within a city or a certain city block, or even searching within the drive time that you get from a certain location. And then finally, there's search where movement is involved. Think about you driving in a certain direction and you want to search for a fuel station for your asset. That means that something that's closest might be behind you and is actually not the most relative option. So you need to be able to search along a route. And that's possible in these kind of APIs as well. Now, how a customer used that in a real-time way was when they did electronic charging points. So this customer provides an electronic charging service for electric vehicles, and they had a big challenge, which was that the devices in the charging stations continuously updated the state of the device. Maybe it was taken, so it couldn't be taken by the users. But also the users in the network, they said, were continuously moving around. So they needed to suggest the right charging station for the right users. And by using these maps and these APIs that were continuously updated, they were able to feed back this information in a real-time way. Now, the second example, which you also saw, is giving you an ETA estimation. What's my travel time to a certain location? And one of the most crucial elements in doing that is using something like a routing API and using the information that feeds back into that. So what you already saw in the example was that devices keep moving around frequently, which impacts things like traffic and understanding blockages in the road. And by incorporating that in a routing API, you can not only understand what's the ETA based on normal traffic conditions, but also what's the ETA right now. Is there something going on? Maybe weather is impacting what's going on. or there's a marathon in the city and there's a blockage on the road that will impact the time that I get there. And that's crucial if you want to make a well-informed decision. Now, the routing API is used in 3 ways when you think about IoT. The most basic one is saying, I have a device and I want to understand within a certain limitation of time where it can get. The second one is actually the opposite, where you're saying, I have a certain destination. Think a drop-off point. And how quickly can the multitude of devices that I have get there so that I can make a decision who to send there actually, or what to send there and in what way. And then finally, there's the matrix version of that. So saying, I have a multitude of locations and devices and I want to continuously understand their relation to each other so that my systems or my algorithms can make a decision based on that. And all of this you can do in a real-time way because every second the situation out there changes and you want to make a decision on that. So to give an example of how a company used that, I'll give an example of an asset management company. So what you see here is a big asset management company that wanted to give alerts to their distribution center when containers came close. And what you see here is during the day when the time changes, traffic conditions change. And what you see here is based on the color is the time it would take you to get to that distribution center. And the time they would send the alerts to their distribution center at changed based on the conditions on the road. And that was crucial for them because what they noticed in the beginning, which was a problem, was that they were sending alerts in irrelevant times. And that completely takes away the credibility of your IoT solution when you're sending things that aren't true. And by using this, by using a routing API, they were able to benefit from that. Now, these were just 2 examples of how you can use real-time location for IoT, but there's, of course, many more. But you can check it out yourself. We have a developer site at developer.tomtommaps.com where you can use these APIs and others for your own use for free. So check it out. Thanks.
Thanks, Arnold. So let's do a quick recap on what we saw today. So we did an overview of the rules engine and talked about the new rules engine capability. And after that, we saw some things about how to enrich messages from AWS through AWS and third-party tools, and when and why would you want to do that. And we got a review from Here Maps and from TomTom. So I'd like to take this opportunity to thank Yuval, and thank Arnold, and thank Yussi, and thank you all for coming today, and we'll be around for questions. Thanks.